11. So the topic is linear regression. Yeah, so in statistics, this concept is very important. It's a basic concept. Let me explain this kind of special data approximation. Oh, all right. Suppose we are given a set of data on a plane. Typically, the data is scattered like, this kind of data. Typical. Yeah. So the data like that, you can see there is a trend. There is some trend. And this trend is very close to a line, a straight line. Okay? Yeah. Here the question is, how to find this line? So that is the basic data approximation question. So we use one straight line to approximate the data. This data has a property, so scattered around some certain trend, line function. Yeah, line trend function. Yeah. But the question is how to find the line. But in order to find that line, because there are many different ways, right? There are many ways for the line, for the line selection. Okay, yeah, for the line selection. Yeah. But we want to find the best one. Yeah. We want to find a line that can approximate the whole set of data points in certain optimal criterion. Some optimal criterion. Okay, yeah. What do you mean the best, right? Because you can define the optimal criterion in many different ways. Yeah. Here I like to give you the most. What's wrong with it? Yeah. All right. Yeah. Here, the most popular way. Yeah. I want to give you the most popular way. So that is called the least square method. Least square method. Yeah. So when you go home, you can find time to study this least square method. Yeah. So today I do not give you the detail, the formulas, how to apply the least square method. Yeah, I just explained the idea, basic idea. Yeah, but oh, yeah. So what's wrong? By accident, I always, you know, by touch something. Yeah. Yeah. But later we will do a simple project. So we will do a, yeah. So after you understand it, so I will give you a very simple project, give you a set of data points and ask you to use, Python function. Yeah. Python has the least square function. So you just apply the least square function to find the solution. Yeah. But I like you do some hands-on work. So let you feel about it. So that will be interesting. Okay. Uh, Python program, write a simple Python program. Yeah. All right. So the least square. So here, because our data points coordinates xj, yj coordinates. All right. Now we want to find the line. Okay. Line function. Line, we need to use a line function, right? Okay. Yeah. Line function, it's a linear function. Yeah, typical line function. Okay. Yeah. Y equals ax plus b. How about that? Okay. All right. So, but we need to determine the coefficient a and b. Yeah. If we can find a and b that satisfy the optimal criteria. Optimal criteria is the least square criteria. That's the optimization. Yeah. Yeah. Let's say optimization criteria. Yeah, not optimal. Yeah. Should be optimization criteria. Okay. Yeah. The least square criteria. Okay. All right. Then so we basically we calculate the distance. We just take, yeah. So here, for each point, let's plug in a xj plus b minus yj. We know if a point is not on the line, then this number won't be zero. Yeah. But because this number could be positive, could be negative. So after we take square, it becomes non-negative. That could be zero. So this square is non-negative. Now, let us calculate the sum of all the squares with respect, for all the data points, j from 0 through m, and we use a symbol S for this representation. Okay, so you can see S is a function of two variables, A and B. So you can change A and B values. When you change A and B values, S would take different values. The question is, for what A and B S takes the minimal takes the minimal, right? Yeah, that is the question. Okay, that is our optimization question. So optimization, problem. And the solution of this problem is the famous least square method. Least square method, the solution. Okay, yeah. So today I do not explain this method. I just give you the problem description. Okay, yeah. For your self-study, you can find a Wikipedia page about this, linear regression topic. Linear regression, and it will talk about the least square method. Yeah, it uses different notation. Comparing with mine. Yeah, yeah. And if you just try your best. If you cannot understand, later I will derive the formula for you. Okay, yeah, yeah. I will derive the formula just for this version. Yeah, for this version. Yeah. And actually, this is the simplest least square, simplest linear regression case. Yeah, because if you look at the Wikipedia page, it may use more variables. Here we only have two variables. We only have two variables. Okay, that's the simplest case. Yeah. So if you study the Wikipedia page, you have more n variables. So that could be relatively hard to understand for you. Yeah. We only need two variables. Yeah. For this class, we will write a program just for two variables. Okay. Yeah. Yeah. So we need to find a solution. Okay. Yeah. Data points given, calculate A and B. So that's our first project. Okay. Yeah. Yeah. So I will prepare the data. Yeah. And I can show you, yeah. I can, because the program just a few lines. So I can show you my program first, and you practice by yourself. Okay. I just show you the graph. Okay. The data points on a plane. And after I determine A and B, I draw the line. I show you the graph. Then I send you my data points. So you write a Python code to calculate A and B and draw the line by yourself. So that's the first practice example for you. Okay? Yeah. Linear regression, least square. Okay? Yeah. Yeah, because this is a very basic, very fundamental for data science. So you have to know this. Okay, everybody should know, linear regression and the least square method before you can study more advanced topics. All right, so that is our first topic today, linear regression. Second one, number 12, polynomial interpolation. This is another fundamental problem. Yeah, very basic. Yeah. We need as a background knowledge. Yeah. Here the question. We are given a set of data points. Yeah. Spread, on the plane. Yeah. Like this. Xj, Yj. Right. Now the question, okay. Find a polynomial of degree n. So here, because we have n points, so that the degree number should be different. Let's say n, different from the number of data points. Degree n, so that is p of x equals a0 plus a1x plus the highest degree term am x to the nth power, such that actually, although it's m, actually you will see, in order to find the solution, in order to make sure we can find a solution, we should use the same n as the data points. So here you can see the data points for j between 0 and n. Here you also see our subscripts of the coefficient from 0 through the n, the same number. Then we can find a valid solution. Otherwise, we may not be able to find a solution, such that p of xj equals yj for all j between 0 and n. So this is a polynomial interpolation problem. So this is the data interpolation condition we talked about before. But here we use a polynomial function to do the interpolation. Okay, the problem can be solved. The solution, I can give you the solution here quickly. But I need to explain a little bit. So why we use polynomial? So why? So here, why polynomial? Okay, this question. We know polynomial, the form polynomial, relatively simple, right? Not very complicated, because you only use addition and a multiplication operation. Okay, addition and multiplication. Operation. Okay, simple. And you can take a derivative. The derivative of polynomial is easy, right? derivative integrals the basic operations we can apply on a polynomial easily. Yeah. So that's the reason we select polynomial. Okay, yeah. All right. And another thing I mentioned before, flexibility, right? Polynomial also provide us flexibility because for any number of points, anywhere on the plane, we can always find a polynomial passing through all these points. How about that? Okay. We can always find that. Okay. Yeah. So you may wonder why we can always find that. Okay. Yeah. So that rely on some linear algebra knowledge. Linear algebra. Because you just plug in, okay? For to interpret the data interpolation condition. We just plug in, okay? A0, the first data point, A1, X0, AN, X0 to the nth should equal to Y0, okay? Second data point, A1, X1, AN X1 to the nth power equals to Y1, and so on. The last one, A0, A1, X sub n, sub n to the nth equals Yn. Okay? Solving this linear system. And this linear system has a unique solution if and only if these locations, x coordinates are distinct. If they are different, then you can always find a solution. Okay, yeah. So this is, from linear algebra. Okay, from linear algebra, yeah. So just some basic knowledge from linear algebra, so you can get this conclusion. Yeah. All right. Yeah. Yeah. But here, I can give you the explicit solution. Yeah. So it's a famous formula called a Lagrange interpolation formula. Lagrange. Yeah. So a French mathematician. Very famous. Let me give you that formula here. Yeah. But actually, you can find also from Wikipedia, this formula. So it's called Lagrange interpolation formula. Okay, all right. Yeah, so let me define Lagrange function, the set of Lagrange, degree n, and then the subscript j, x. Yeah. So it is a special polynomial. So you can see, for j, each j, product notation. So this capital pi, this is a product notation. K equals j. Actually, okay, sorry, not equal to j. Yeah. K cannot equal to j. Okay, not equal to j. So x minus xk and xj minus xk. So you can see the denominator cannot be 0. So k cannot be j, all right? Yeah. But j is fixed. J is fixed. K change, yeah. K change, yeah, changes. Okay. How k changes? Yeah. Because when we choose k, we select from 0, 1, 2. Yeah. And here, when we had j, skip. K skip this j. Then, take all the other points. Yeah. From 0 through n, but just to skip that j. Then you take product. Okay. Product of the, this fractional form. Yeah. But the variable, x is the variable. The variable is at a denominator, at a numerator. Yeah. And all the other x coordinates, they are numbers. Yeah. So they are not variables. They are numbers. Yeah. So this is the Lagrange. Lagrange, we call it the basis function. Lagrange. These are the, for j between 0 and n. So you have n plus 1 called, basis functions. Okay, Lagrange basis function. So the definition of Lagrange, yeah. After this definition, yeah. So there is a special property of Lagrange basis functions property. Interpolation, the special property, yeah. So that is ln j xj equals 1. If you plug in xj, you can see equals 1. Okay, yeah. All right, yeah. You plug in, numerator, denominator the same. So that's 1, right? The product of all ones, right? Yeah. Because each fractional form is 1, you multiply n times. So that's 1, okay? Yeah. And L and J xk equals 0 for k not equal to j. Yeah. If you plug in any k, 1k, because the one of the numerator number must be 0. Okay? Yeah. K, for any k, one of the numerator number must be 0. So the whole thing is 0. Okay? Yeah. So that's simple. All right. So this property is very nice. Yeah. So why this property is so important? Because we can write the polynomial interpolation formula in this way. So here is the polynomial interpolation formula. Okay, yeah. So the solution of the polynomial in our previous slide can be written as summation j from 0 through n yj multiply that L comma n comma j x. That's a polynomial, right? That is a degree n polynomial. Okay, yeah. Degree n polynomial. And this degree n polynomial, you just plug in xj, p of xj, yeah. Summation of the numbers, okay, yeah, j. All right. When, yeah, because yeah, sorry. Here, yeah, it's better because if I use the notation j here, we get confused. How about we use k here? Okay, we use k here. Okay, okay, all right, okay, all right. Then we plug in j. Okay, yeah, because when k not equal to j, all 0, right? 0 plus 0 plus dot dot dot, right? But when k equals j, it becomes 1, this L part equals 1. But when k equals j, this yk becomes yj, right? Yj times 1, all right? After that, all 0. All zeros, okay? Yeah, yj times 1 equals yj. Yeah. That's our interpolation condition. P of xj equals yj. And this is true for all j between 0 and n. So that tells us this formula gives us the polynomial interpolation condition. So that is the famous Lagrange interpolation formula. Hundreds of years ago, yeah, Lagrange, a French mathematician, found this formula. Okay, yeah. All right. So here you can see we get some nice polynomial data interpolation formula. All right. Next, yeah, summary. Yeah, I like to make some comments about this method. All right. commons for polynomial interpolation. Okay, yeah. First, when the number of data points is large, the degree of the polynomial is also very large. Okay, our first observation. Is it good or not? Okay, so this is a simple property of this method. The question is, this property is good or not? Okay. Yeah. Yeah. The answer is not good. Okay. Not good. Why? Because if the degree of a polynomial is very high, the error, the evaluation error, polynomial evaluation error could be out of control. Why? Out of control. Think about, when we evaluate to the, 1,000. Okay, yeah. Even because when we plug in x, many times we may have some small error, right? Yeah. Let's say we like to plug in, for example, 3, but due to some reason, there is some, very small, possible small error, right? Yeah. So small, we may feel the small error may not cause big problem, but when you raise to 1,000, when the degree is so high, the error part, the extra, error part could be accumulated to be very large, out of control. Okay, you cannot ignore the error part. All right, yeah. So that won't be good. That make our calculation not stable. We won't get a stable calculation with such a high degree polynomial. Because in computer, we cannot use very accurate floating point numbers, even double precision. We need to truncate some digits. Yeah. We have to truncate certain number of digits. But when you truncate, that error could be accumulated. And after you raise to power of high degree power, that error is very big, too big to be ignored. Okay, yeah, so that's not good. So that's one thing. Another thing. Yeah, let me look at the time we have today. Yeah. Let me just talk about the last property. Yeah. Another thing, yeah, when the degree is high, there is another problem. When the degree is high, there is a lot of fluctuation in the curve. Yeah, let me explain the phenomenon here. All right. Suppose this is XY axis. Okay, yeah. All right. Polynomial degree m, yeah, we know. We look at the, simple polynomial example here. Let's say 1, 2, 3, 4, 5, 6. Yeah. Let's consider degree 6 polynomial with these 6 numbers as the roots of the polynomial. So that is, the polynomial is 1 times x minus 2 times x minus 3 times x minus 4 times x minus 5 and x minus 6. Okay, all right, yeah. All right, then let me draw the curve something like this, because you need to passing through all these points. All right, and that's the typical curve like that. But here, our degree in this example only equal to 6, right? 6, you can see up and down, change directions, certain number of times. Think about if the degree is 1,000, you need to, up and down change 1,000 times. So the fluctuation is very big. Okay? Yeah. So that kind of approximation is also not very, very good. Okay? Yeah. Because the fluctuation like this, it's not a, simple approximation. So you can pass through. So things like that. Okay. Yeah. So here, let me draw another, because for some data points like that, okay, we expect to have the approximation like that. But the high degree polynomial, you give the approximation like with a lot of fluctuation. So that's not what we want, right? too many wiggles. So that's not good for our applications. Okay, yeah. So you can see as a conclusion, the polynomial approximation is not a good choice, the conclusion. Okay, so although the formula looks pretty smart, okay, yeah, smart idea, but not practical. In real world applications, polynomial approximation is not practical. So we cannot use that. We cannot use this method in real world applications. So we have to drop it. We have to consider a better solution for our function selection, interpolation function selection. Okay. All right. So let me stop here. Next time I will talk about, better selection for data interpolation. Okay. All right. So let me stop here today. Yeah. So, and I will also upload the video. Yeah. Yeah. I haven't posted in our Canvas.